Number 128A involves us using something called a mole ratio. And a mole ratio is another type of conversion factor. In this case, it's going to allow us to go from moles of potassium permanganate, KMnO4, to moles of oxygen. Now you get the mole ratio here by looking at the chemical formula of KMnO4. If we had an individual formula unit of KMnO4, right, we would have 4 atoms of oxygen. We can scale that up and say that if we had a mole of KMnO4, we should have 4 moles of oxygen. In this case, if we want to cancel out our KMnO4s and get oxygens, we want to have our conversion factor with oxygen on the top, just O on the top, and KMnO4 on the bottom. So we're starting with 0.250 moles of potassium permanganate. We know there are 4 oxygens for potassium permanganate. Those will cancel out and you end up with your final answer here, that you have 10 moles of oxygen in your 2.50 moles of potassium permanganate. Up until this point in the homework, when we've worked with the molar mass of things, we've only dealt with individual elements. We can expand our molar mass to deal with compounds as well. And the way you can figure out the molar mass of a compound is by determining the molar mass of each of the elements that makes up the compound and the number of atoms of each element in that compound. So for HNO3, which is nitric acid, we know that there is 1 hydrogen, there is 1 nitrogen, and there are 3 oxygens. To determine the molar mass of this, we add up the molar mass of our 1 hydrogen, that's 1.008 grams, our 1 nitrogen, 14.007 grams, and our 3 oxygens. So we multiply our molar mass of 1 oxygen by 3. Adding all these together gets us our overall molar mass for nitric acid, which is 63.02 grams per mole. And this molar mass is important because we can use that as a conversion factor for going back and forth between grams of a compound and moles of a compound instead of just working with individual elements. And that's exactly what we do in number 142 here. So number 142, you want to determine the number of molecules of ethanol, which has a chemical formula of C2H5OH, C2H5OH, in 47.0 grams of this stuff. So in order to do this, right, we're going to have to make 2 conversions. You're going to need to go from grams to moles and from moles to molecules. Previously, we went over the conversion factor you use when you go back and forth between grams and moles. That's molar mass. So to solve this, we're going to need to know what the molar mass of ethanol is. And you do that by adding up the molar masses of each of the elements that make up ethanol and taking into account the number of atoms of each of those elements. Right? If you do that, that'll give you 46.069 grams per mole. Okay, once we get our number of moles, we need to go from moles to molecules. You do that using Avogadro's number. Again, the trick here is trying to remember how you can arrange these conversion factors to get you the units you want. So the first step, going from grams to moles, you want to cancel out grams, so you want grams in the denominator. So that means you're going to want to divide by the molar mass of ethanol. Okay, that'll give you some number of moles. From there, to get molecules, you multiply by Avogadro's number, because by doing so, you'll cancel out your moles and get molecules. If you do that, you should end up with 6.14 times 10 to the 23rd molecules of ethanol. Number 143 is a lot like number 142, except we're adding on an additional step. We need to use the mole ratio in this one. So number 143 asks you what mass of iron 3 chloride contains 2.35 times 10 to the 23rd chloride ion. Formula for iron 3 chloride. That Roman numeral 3 means you have a charge of Fe3+. If you look at the periodic table, you can find out that the most likely charge for a chlorine ion is 1-. Iron 3 chloride is an ionic compound, so when you come up with its formula, you need to worry about balancing charges. In this case, you need 3 chlorines to balance out the charge of 1 iron. So our formula is going to be FeCl3. That's important because we needed to solve this problem. Right? We're just given chlorine ions to start off with, and we want to go from chlorine ions to the mass of this compound. Okay, we know from our formula that there are 3 chlorine ions per iron chloride here. So we can use that as our mole ratio. We can do the same thing with number of ions. Okay, so we start off with chlorine ions. We want to go from chlorine ions to FeCl3. In order to do that, we need to cancel out our FeCl3s and get Cl minuses. Now I just realized I made a mistake when I showed my work here, so if you look at it now, the conversion factor should be a little bit different. Anyway, we want to cancel out the Cl minuses. So we want Cl minus in the denominator, and we want iron chloride in the numerator. Earlier I said there are 3 chlorines per iron 3 chloride. So our mole ratio should look like this. We want to cancel out the Cl minuses. We want our Cl minuses in the denominator. From here, we've got number of formula units of FeCl3. We want to go from formula units to moles. In this case, you divide by Avogadro's number. That'll cancel out your formula units. So really, this would be 1 iron chloride formula unit over 3 Cl minus ions. So a formula unit would cancel out there, and you get moles. Once you get your moles, you can go to mass by multiplying by the molar mass of FeCl3, which is 162.197 grams. Moles cancel out, you're left with grams, gives you 21.1 grams. Number 149 is similar, but we're working in the opposite direction. We want to know how many sodium ions there are in 25.0 grams of sodium chloride. So sodium chloride has the formula of NaCl. You can figure that out by balancing the charges. Na has a most likely charge of +1, and Cl has a most likely charge of -1, so you need one of each to cancel each other out. So we can start off in this problem by going from grams to moles, because you can go in a lot of different directions for moles. Use the molar mass of sodium chloride to determine this. So that molar mass is 58.44 grams. You can get that by adding up an Na molar mass plus 1 Cl molar mass. So now our grams have canceled out. From here, you know that each sodium chloride has 1 sodium ion. So likewise, 1 mole of sodium chloride should have 1 mole of sodium. So our conversion factor here is just 1 over 1. Our NaCl's cancel out. Once you know the number of moles of sodium, you can translate that to ions by using Avogadro's number. We want to cancel out moles, and we want to get ions. So you're going to multiply by Avogadro's number. Doing so should yield 2.58 times 10 to the 23rd ions.